Okay, so in this example, I want to calculate the work done by the gravitational force, right, which is basically the work done by the weight, right? The weight would be the force. Um, when lifting this object, so I have an object here has a mass 3 kilograms, and it's undergoing this vertical displacement, right? So it's going from an initial position of 1.5 meters above the ground to a final position of 4.5 meters above the ground. And I want to calculate the work done by the gravitational force as it undergoes that displacement. Then what I want to do is calculate the change in potential energy. So notice that this change its vertical position, right? So it has a change in potential energy. So I want to calculate the change in potential energy of this object and then compare the two. Okay, so first of all, we know that the change in the y position, right, the displacement in the y direction is going to be y2 minus y1. So that'll simply be 4.5 minus 1.5, which is going to be 3, right? So 3 meters. All right, so we have that. We want to find the work done by the gravitational force, which is the weight. Well, remember, in general, it's going to be the magnitude of that force times the displacement, which is delta y in this case, times the cosine of the angle between those two vectors. But since the weight is acting down, right, the gravitational force weight is acting down and displacement is up, the angle between them is 180 degrees. So this is really cosine of 180 degrees. So, and then I can write the weight as really just mg, right? mg times delta y times cosine of 180. Okay, remember, cosine of 180, we'll do it right here, is equal to -1, right? So if I plug everything in, the mass is 3, g is 9.8, the displacement is going to be 3, right? Delta y was 3, and then cosine of 180 is -1. This turns out to be negative 88.2 joules. And it makes sense, right? Because the weight, the force due to the gravitational force, the weight, it's opposing the displacement, right? So it's doing negative work. As the object rises from here to here, the weight is doing negative work on the object. In fact, it's doing negative 88.2 joules. Okay, now let's calculate the change in potential energy as the object moves from the initial position to the final position. Well, remember, change in potential energy, and this is like gravitational potential energy, is equal to the final gravitational potential energy, so at position 2, minus the initial, which is at position 1. So remember, gravitational potential energy is simply mg y final, so this would be like y2 minus mg y initial, which is y1. I could write this, I could factor out the mg and write this as y2 minus y1, but y2 minus y1 is simply going to be delta y. So if you want, you could write this as mg times delta y. And if I plug everything in here, I'm going to get, so this is 3 times 9.8 times delta y, which is 3. I'm going to find that that equals 88.2 joules. Notice that these have the same absolute values, right? The work done by the gravitational force, by the weight, is negative 88.2, and then the change in potential energy, gravitational potential energy, happens to be positive 88.2 joules. So they're basically the same value, but they have opposite signs. And it turns out that the work done by a conservative force can always be written as negative the change in some potential energy. So in this case, and this is sort of the key point that I'm trying to make here, the work done by the weight, by the gravitational force, is equal to negative the change in gravitational potential energy. Okay, and in general, the work done by a conservative force, say, is equal to minus the change in some potential energy. It may have a different name, but because in our case, it was a gravitational force, it's a change in gravitational potential energy. So it's always equal to the work done by a conservative force can always be written as negative the change in some potential energy. And the case that we're going to deal with in this class is really just gravity. So we're going to have this case, the work done by the conservative gravitational force, right? The weight is going to be equal to minus the change in gravitational potential energy. Okay, so knowing that, this will help us solve, different types of problems. Let's go back. Let's revisit the work energy theorem. Okay, so remember, the work energy theorem says that the net work done is always equal to the change in kinetic energy, right? We've been doing several problems using that, the work energy theorem. But let's split up that net work into work done by conservative forces and work done by non-conservative forces. So I'm just splitting this up. Instead of net work, I'm calling it the work done by conservative plus the work done by non-conservative. And then to save a little bit of writing here, I'll just call the conservative, I'll call it C, and non-conservative NC. So the net work is equal to the work done by conservative WC plus WNC, the work done by non-conservative forces. So now we can rewrite this work energy theorem as the left-hand side now becomes the work done by conservative forces plus the work done by non-conservative forces. That has to equal the change in kinetic energy. Okay, so all I did again is I rewrote the net work as the sum of these two, the work done by conservative plus the work done by non-conservative forces. Now, let's assume that only conservative forces are acting on a system, right? Or if there's non-conservative forces, they're not doing any work on the system. Okay, and I'll explain that in a second, because you could have a situation where you have a non-conservative force, but it's just not doing any work because the force is perpendicular to the displacement. So that could be a case. So assuming that you only have conservative forces acting on a system, that means the work done by non-conservative forces is going to be zero, right? Like this term, if I assume there's only WC, then this term will be zero. So then I have the work done by conservative forces equal to the change in kinetic energy. But we know that the work done by conservative forces can always be written as negative the change in a potential energy. So in the left hand, I can replace this WC here by negative the change in potential energy equals the change in kinetic energy. And then if I assume that this work done by conservative force, assume the only conservative force acting is gravity. For our examples, we'll just assume it's gravity. Then that means this negative change in potential energy is really negative change in gravitational potential energy, okay? If I add this term to both sides, right, then I can write this as zero, because if I add it right to the left-hand side, it'll cancel. If I add it to the right-hand side, I'm going to get change in kinetic energy plus change in potential energy. But remember, change means final minus initial. So if I expand this out, this is going to be the final kinetic energy minus the initial kinetic energy plus, and then change of potential is final potential energy minus initial potential energy. But kinetic is simply 1/2 mv squared, and potential is mgy. So I can write this as 0 equals 1/2 mv final squared minus 1/2 mv initial squared plus mgy final minus mgy initial. And now usually what we do is we bring the negative terms to the left-hand side so they become positive. Like if I add 1/2 mv initial squared and add mgy initial to both sides, then I'm going to get this, right? I'm going to get ke initial plus pe initial equals ke final plus pe final. Or 1/2 mv initial squared plus mgy initial equals 1/2 mv final squared plus mgy final. Well, it turns out that this sum of kinetic energy and potential energy has a special name. It's called the mechanical energy. So really what this is saying is that the mechanical energy initial equals the mechanical energy final. So if you have no non-conservative forces, or if there are and they're not doing any work, so in other words, if you only have to take into account your conservative forces, like gravity in our case, then it turns out that the mechanical energy is conserved. It's the same. It has the same value. The mechanical energy initial equals mechanical energy final. Okay. So even like the way to think about this is you could be gaining, say, kinetic energy because the velocity is increasing, but then you're losing potential energy. So that sum of the two is always the same value. Okay, that's what it's saying. So if we have no non-conservative forces acting, and usually by a non-conservative force, we think of like a push or a pull by a tension or friction, right? So if we assume there's no friction acting, no pushes or pulls in some any old way, and the only force acting really is gravity, the gravitational force, then we have this situation where mechanical energy is conserved. Okay, let me give you some examples of this. So I'm going to first start with a sort of a classic example, and it's that of a roller coaster. Okay, so here's the situation. I have this roller coaster. It's moving initially with some velocity or some speed, right? 30 meters a second to the right. And I'm going to call this point C, the initial position here. And I'm going to call that the height here. This is like my reference point. So this would be y equals 0. And we know that the mass of the roller coaster is 200 kilograms. So it's going to move through this roller coaster track. And what I want to do is I want to find the speed of the roller coaster at this position, A here. So when it's at the bottom of this hill, and I want to find the speed again when it's at the top of this hill at B here. Okay. We're assuming there's no friction, right? So there's no frictional force acting, opposing the motion of the roller coaster. If there were a frictional force, then we wouldn't have conservation of mechanical energy. So we couldn't actually use conservation of mechanical energy. There's different ways of solving it if you start including non-conservative forces, and we'll show you an example of that in a minute. But for this example, we're assuming there's no friction. Now, so the only forces that are really acting on the roller coaster here are the weight, right, which is the gravitational force, but we know that the work done by the weight, since it's a conservative force, can be written as a change in potential energy. Okay, so that will be taken into account. The work done by the weight there will be taken into account when we talk about change in potential energy. We also have a normal force here, right? A force that the track exerts on the roller coaster perpendicular to the track. And you might say, wait a second, that is not a conservative force, right? That's a non-conservative force. But for any instant, like wherever this roller coaster is, let me just draw it randomly over here somewhere. The normal force is going to be perpendicular to the track. And the displacement, if I do like a little delta x just for that instant here, it'll always be parallel to the track, right, at each instant. So therefore, the work done by that normal force, by that non-conservative force, is always going to be 0 because it's always at a 90-degree angle, right? If you look at this angle here, this is always 90 degrees. So that normal force is not doing any work on this roller coaster. It's not tending to speed it up or slow it down. Okay. And that's if you look anywhere. Like if I do it here, I just pick another spot here, the normal force is like this. And the displacement, a little tiny displacement on the track, is this way. So again, those are at 90 degrees to one another. So the normal force does not do there's no work done by the normal force acting on this roller coaster. So that means the only force acting is the weight here. And since that's a conservative force, then we can apply the fact that mechanical energy must be conserved. Okay, so just by using that argument, normal force does no work. The only force acting is this conservative force, the gravitational force, which is the weight. We know that mechanical energy is conserved. Well, this is nice. Okay, so we're assuming ME, mechanical energy, is conserved. And we have no friction, right? Otherwise, that would goof things up. So we're assuming friction is negligible. So what I can do here is I can calculate the mechanical energy, say at point C. I'll say a C there. So the initial spot of the roller coaster. And that's got to equal the mechanical energy at point A or at point B. I'll just write, for right now, I'll do mechanical energy at point C has to equal mechanical energy at point A. Well, remember, mechanical is kinetic plus potential. So I can say kinetic energy at C plus potential energy at C has to equal the kinetic energy at A plus the potential energy at A. But remember, kinetic energy is 1/2 mvc squared, right? The velocity at C, or the speed at C squared, plus mg, and then we'll have the position at C. That's got to equal the kinetic at A, which is 1/2 mva, the velocity at A squared. And that's what I'm looking for, right? I'm looking for the velocity at A plus mgya. Okay, what do we know? Well, we know the velocity at C. First of all, we know the mass is 200 kilograms. We know the velocity at C, that's given, that's 30, right? That's the speed really at C. We know the position, the vertical position at C, y of C, is 0, because we're saying that's our reference point. And we know the y at A, since it's down 10 meters, it's going to be -10, right? And we're looking for the velocity at A. That's what we want to find. So basically, this is like a plug and chug problem now, right? If I plug in all those values, so I have 1/2, 200, right? That's the mass, times 30 squared, plus I have 200 times 9.8 times y, the position at C is just 0, right? Because that was the reference point, equals 1/2 200 times the velocity at A squared plus 200 times 9.8 times -10. That was the position at A, y of A, right, which is -10. So if you work this out, let's see, you're going to have 9,000 or 90,000 plus 0 is equal to 100 VA squared minus 19,600. And then if I solve this for VA, so I'm going to add 19,600 to both sides. I'm going to get 100. I'll just write on the left-hand side here. 100 VA squared is equal to, what's that going to be? I guess 109,600. Now I'll divide by 100. So I have VA squared is equal to, that's going to be 1096. And then finally, to get VA, I need to take the square root, right, of both sides. And I want the positive root. So VA here is going to be 33.1. If you take the square root of 1096, it's 33.1 meters per second. So that's going to be the velocity or the speed of that, because remember, speed is just the magnitude of the velocity at position A, which makes sense, right? It's moving at 30, it's going down a hill, you would expect it to speed up, and we're saying that at A here, it'll be slightly faster, like 33.1 meters per second. Now we also want to calculate the velocity or the speed at position B here. And since it's going way up this hill here, you expect it to be slower, right? So what's happening here is, here it's losing potential energy, but gaining kinetic. Here it's going to be losing potential. It's going to be gaining potential and losing kinetic. So it's going to be going slower here. But the sum of those two, the sum of the kinetic and potential, are always the same, right? For any location that this roller coaster is on, any part of the track here, the sum of the potential and kinetic is the same, right? The mechanical energy is the same. So again, here we're losing potential, gaining kinetic, which means you're going faster. Here, we're gaining potential and losing kinetic, which means you're going to be going slower here. So to calculate the velocity at point B, or the speed at point B here, I can say the mechanical energy at C equals the mechanical energy at B, or the mechanical energy at A equals the mechanical energy at B, right? It's going to be the same regardless. I think I use the mechanical energy at C equals the mechanical energy at B. So it's exactly the same thing we just did here, except now I'm applying it to point B. So if we do this, I'll do it over here. I have mechanical energy at C is equal to the mechanical energy at B. So this is going to be the kinetic energy at C plus the potential, right? The gravitational potential at C is equal to kinetic energy at B plus the gravitational potential energy at B. So I'm going to have 1/2 mvc squared plus mgyc is equal to 1/2 mvb squared plus mgyb. And if I plug in, this is 1/2 200 times 30 squared. Remember, yc was 0, right? So that potential energy initial at C is 0. Then this is going to be 1/2 times 200 times, we're looking for VB, so VB squared, plus 200 times 9.8. And then YB is 40, right? Because it's positive 40 above the reference point. So this is 40. So if you work this out, this will be 90,000 again, right? Is equal to 100 VB squared plus 78,400. And then if I subtract 78,400 from both sides, I'm going to have 100 VB squared is equal to 11,600. Now divide by 100. So divide by 100. So VB squared is equal to 116. And now finally take the square root, right, of both sides. Square root. We want the positive square root. So VB in this case turns out to be like 10.8 meters per second. So that would be my speed at position B, right? And notice it's much slower, right? So initially it was 30, then it sped up, right? At position A, it was going faster. It was like 33, I guess. And then at position B, it's more like 10 meters per second. So again, we lost potential energy, but gained kinetic energy. Here we're gaining potential energy, but losing kinetic energy, right? But that sum of the two is always going to be the same. Okay, let me do one last example here. So this one is a little bit trickier. So this one says, let's say you have a 60.0 kilogram skier with an initial speed of 12 meters per second, coast up a 2.50 meter high rise. So in other words, the height from their original position, their height straight up is 2.5 meters. They're trying to get to this higher level here. And we know her initial speed is 12 meters a second, right? And we want to know the final speed when she's at the top level here, when she's 2.5 meters up. What is her final speed here? But now we actually have friction. So we're not saying it's frictionless. We're saying there's friction between the skis and the snow. And we're told that the coefficient of kinetic friction, so mu k, is 0.080. So basically what's going to happen here is that when she is going up the hill here, there's going to be a frictional force, right, which is doing negative work. That's going to slow her down. Plus she's gaining potential energy. That's also going to slow her down. And we want to figure out that final velocity here. So we can't quite use conservation of mechanical energy because there is a non-conservative force acting. There's friction acting. right? However, if we change the formula slightly so that we include the work done by the non-conservative force, which is the work done by the frictional force here, then we can solve this problem. But it's a little bit trickier. So let me sort of outline this. So what we're going to say, remember, the net work is equal to the change in kinetic energy. But I can break net work down into the work done by non-conservative plus the work done by conservative. And that's going to equal the change in kinetic energy. And so in our case, our only conservative force acting is going to be the gravitational force, right? The weight. So then I can further break this down. I can say, well, I have work done by non-conservative, which I can't do anything with. The work done by the conservative, the gravitational force, is equal to minus the change in potential energy. And that's equal to the change in kinetic energy. If I bring this term to the other side, right, the potential energy, I can write this as the work done by non-conservative force is equal to the change in kinetic energy plus the change in potential energy, which actually is the change in mechanical energy. So we were saying earlier, right, if you have no non-conservative forces, the change in mechanical energy was 0. But now it's not equal to 0. It's equal to the work done by any non-conservative forces that you have. Okay, again, this is a little bit trickier than some of the problems we've done in the past. Okay, so let's see what's going on here. What are the forces acting on the skier? And really, we're only interested when they're going up that ramp, right? The forces acting on the skier when they're going up the ramp. Oops, they just lose it. Okay, so let's say this is our ramp. And we know, let's see, this angle here is 35 degrees. We have the skier. Going up the ramp. What are the forces acting on the skier? Well, their weight is acting down, right? That's the gravitational force. So that is a conservative force. There's a normal force, which acts perpendicular to the ramp. But that's not going to do any work, right? Because remember, the displacement is going to be like up the ramp here. But then we have this frictional force. And since they're moving, it's a kinetic frictional force. That is a non-conservative force, and it is going to be doing work. In fact, it'll be doing negative work, right, on the skier as they go up the ramp, as she goes up the ramp. Okay, so let's figure out what the magnitude of that kinetic frictional force is going to be. First of all, I need a coordinate system, right? I'm going to say going up the ramp is positive x. So perpendicular to the ramp will be y direction. So what I want to do in order to figure out that normal force, I want to use Newton's second law and sum the forces in the y direction. And that's going to be MAY, which is 0 in this case because the skier is not leaving the ramp, right? They're just going up the ramp. They're not leaving it in the y direction. So sum of the forces in the y. So I have the y component of the normal force plus the y component of the weight plus the y component of the kinetic frictional force. That's got to equal 0. Okay, what is the y component of the normal force? Well, if you look at this, and I'll draw it clearer. This is like my axis, my y-axis, and then this would be my x-axis. So how much of that normal force is in the y direction? All of it, and it's in the positive y direction, right? So that's going to be all of n. Now, what about the weight? Well, the weight's a little more complicated here, right? I need to find the components. I want the y component of the weight. So if I project this onto the y-axis, I want this component. This is like WY. And this angle, it turns out, so the angle it makes right here is also 35 degrees. And if I want this one later, this is going to be WX. Okay, so it turns out that Wy is going to be first of all, it's negative, right? And it's going to be mg. Now, if we use a reference angle, then if that's 35 degrees, the reference angle over here would be 90 minus 35, right? Which is 55 degrees. Or, I mean, we can do either. If I use that 35 degrees, then you have to be careful. The y component now is going to involve the cosine, and usually involves the sine, right? But in this case, it involves the cosine because I'm going to use that 35 degrees. So it's minus mg times cosine of 35 degrees. And in wx, well, it's pointing down, negative x direction, right? So it's negative, and it's mg times sine of 35. Okay, or you could say wy is minus mg times sine of 55, and wx is minus mg times cosine of 55. That'll give you the same answer. Okay, so in this case, wy here is going to be minus mg cosine of 35. And then what's the y component of the frictional force? That's 0, right? It's only acting in the x direction. So the normal force here is going to be mg cosine of 35 degrees. And we know that the frictional force, kinetic frictional force, is mu k times n. So this will be mu k times mg cosine of 35 degrees. Okay, so that's the magnitude of that frictional force. Now, this person, right, she's moving up this ramp here. We need to figure out how far she's moving, right? Because that's going to be the displacement. So we need to figure out the length of the ramp. So the displacement which is delta x, is the length of the ramp. Okay, so how do we figure out that? Well, we can just use a little bit of trigonometry here. Right, we know this angle is 35 degrees. We know the height change. Remember, they're going up a vertical distance of 2.5 meters, and we're looking for delta x here. So what trig function relates opposite the angle and hypotenuse? That's going to be sine, right? So sine of 35 degrees equals opposite divided by hypotenuse. So therefore, the delta x, if you solve for delta x, it turns out it's going to be 2.5 divided by sine of 35 degrees. And that turns out to be 4.36 meters. Okay, so that's our displacement. Okay. I need to go on the next page to finish this. So remember, the work done by the non-conservative force, which is the friction, so I'll just write it here, is the work due to the frictional force, Fk. So we had that the work done by the non-conservative force is equal to the change in kinetic energy plus the change in potential energy. If I write this out, then the work done by non-conservative force is equal to, this is 1/2 mv final squared minus 1/2 mv initial squared plus mgy final minus mgy initial. Okay, the work done by the non-conservative force, which is the work done by the frictional force, that's equal to the frictional force times displacement times the angle between them, but the angle between them is 180 degrees, right? And remember, this is like -1. So this is going to be like negative, and then FK was mu k mg cosine 35. So this is mu k mg cosine of 35 degrees, and then also have a times delta x there. So that's the work done by the frictional force, which was the non-conservative force. Okay, so now if I put this all together, on the left-hand side, I have that term, right? So I have minus mu k mg cosine of 35 degrees times delta x. That's got to equal 1/2 mv final squared minus 1/2 mv initial squared plus mg y final minus mg y initial. We want to solve this for v final. Right, remember what we're trying to find here. I'm going to go back to this picture. We're trying to find the velocity of the skier when she's at this position, right when she reaches the top here. Right, what is her final velocity, right when she reaches the top? So she has this velocity right before she goes up this hill of 12. She's going to lose some energy here, right? Due to, well, first of all, because she's gaining potential, she's losing some kinetic energy. And also this frictional force, right, is doing work, negative work on her. So she's losing energy due to there too. And we want to figure out where her final velocity is at the top here. Okay, so basically I just need to solve this for the final. So it's a little bit of algebra here. What you could do, you could multiply everything by 2, I guess, first. So then this will be -2. Let me do it back in black again. So -2 mu k mg cosine of 35 degrees times delta x equals mv final squared minus mv initial squared. Just multiply everything by 2. 2m gy final minus 2m gy initial. Okay, so if I solve this, for v final squared, let me solve it first for mv final squared. All right, and then we'll divide everything by m. So I have mv final squared equals, I'm going to have that term on the left-hand side that stays there. So this is just a little bit of algebra you have to work through. And everything else is going to move to the left-hand side, right? So this will become plus mv initial squared minus 2mgy final, and then plus 2mgy initial. It's going to change all the signs. And now I'm going to divide both sides by m. So all the m's will cancel here, right? They're in every term, so I can factor it out and then divide it. And then finally, I can take the square root of both sides. So you're going to have v final is going to be the square root of -2 mu k g cosine of 35 delta x plus v initial squared minus 2gy final plus 2gy initial. And then I can plug in. So -2. Mu k was 0.08, right? 0. G, of course, is 9.8. Then I have cosine of 35 degrees. Delta x, remember we had to figure out the length of that ramp, which is 4.36. Plus v initial, that was 12, right, squared. Minus 2 times 9.8. Y final was 2.5, right? The hill was the top part of the hill was 2.5 meters above the ground. And then y initial, that was 0, right? Because that was our reference point. So this is just going to be 2 times 9.8 times 0. So that term's not going to matter there. So if you work this out, right, plug into your calculator, just carefully make sure you're using order of operations, do this carefully. You're going to find that the final velocity is 9.46 meters per second squared. Okay, so granted, this was definitely a more challenging problem, and it was because we did have a non-conservative force here, right? The force due to friction. So we had to include it in our work energy theorem so that we had this work done by that non-conservative force, by the frictional force, and that turned out to be equal to the change in kinetic energy plus the change in potential energy. When you don't have any non-conservative forces, then this is really nice because then this is just equal to 0, right? The work done by non-conservative force would be 0. But in this case, we did have it, so it has to be included in the equation. Okay, definitely a more challenging equation, more challenging problem than what we have when we have just pure conservation of mechanical energy. Okay, so that's all I really wanted to talk about in terms of work and energy. Great, thank you.